Thanks for having me here, and it's great to be talking today about scene representations for autonomous driving. So I'm Krishna, as I'm a Ph.D. student at Mila, and like today my talk is going to be based on the premise that just all of pretty much most autonomous driving approaches today are based on. The usual way autonomous driving is done is you build a high resolution or high definition map of the area you want to drive in. And this is where I really start my talk. And I'll talk about a few issues as to what's issues with maps and then how we might be able to overcome them. And yeah, so most autonomous driving systems need high resolution maps of the area they drive in. And these maps are often built by first driving a car around an environment, collecting lots and lots of sensor data, and then first reconstructing geometric maps of the environment. But after getting this geometric reconstruction, often you have humans in the loop that annotate lots of things like, this is a lane and this is how you need to turn at this particular intersection. And then there's all sorts of other things like road signs and things that humans would want cars to know about. And this process becomes very painstaking. The moment you think about scaling autonomous driving to lots and lots of cities, so you have each country and each city or maybe province has their own sort of restrictions or style of putting up road signs or like driving conventions and things like that. And the typical way this works is once you have this high definition map at inference time, or like at the time when the autonomous car has to actually drive from A to B, you perform a localization step, which localizes the car within the map. And then all of the subsequent planning and control is performed on the basis of this localization, plus also some of the other dynamic actors you observe. For example, cars or other pedestrians that are not mapped but occur during the run. So there's a few issues here with having these pre-built high definition maps. So scalability is a very big concern because these maps can often get to gigabytes or in some cases terabytes for large urban regions. And these maps, importantly, they need to be maintained because things can really go out of date really quickly if roads get closed or repaved, lanes get changed, and so on. So since there's humans in the loop, the maintenance or update time is exacerbated by this fact. And the other important problem that I'll focus more in the second half of the talk is coverage, because most roads in most countries are actually not urban centers, but they're rural lanes. So for the continental US, there's a stat on the Transportation Department webpage, which says more than 70% of roads in the continental US are actually rural roads. So to actually be able to scale autonomous driving approaches to span a wider geographic region, you need to be able to handle rural roads and make sure they don't go out of date very rapidly. So there's like that spectrum where you have really high definition maps of urban centers, and these maps are typically owned by a few closed source companies and so on. But there have been other efforts to make publicly accessible and editable maps. So one particular effort is the OpenStreetMap. It basically does what Wikipedia did to encyclopedia articles. So OpenStreetMap is basically an editable geomap of the world. And then it's not just geometric information, but it has a lot of other metadata layers. So you can go in and tweak OpenStreetMaps. You can add attributes like widths of roads, and you can add things like stop signs and all sorts of other information. And since it's crowdsourced, it's easier to scale, but also it comes with a few caveats in that it's crowdsourced. So you have no control over the quality of or accuracy of the resulting map. But the reason I introduce OpenStreetMaps is I'm going to talk about two recent efforts in which we leverage data that's publicly available, but also inherently noisy or inaccurate. And we use this in the first application I'll talk about is using this for improving perception. And the second half of the talk will actually focus on a full self-driving task for rural roads relying on OpenStreetMaps. So yeah, the first half or so of the talk, I want to focus on one of our recent efforts on what we call Amodal bird's eye view layout estimation. So this paper titled MonoLayout was this was a paper we published about a year and a half ago now. And the idea here is to think about a representation that you can use for a lot of driving decisions. And we think a bird's eye view plane is a good representation because a lot of driving decisions get taken in the two-dimensional ground plane that you're driving on. A lot of other vehicles and pedestrians, they move along this ground plane. So this makes it a natural choice. And the task in this paper is given an image of image captured by like a dashboard style camera, you want to generate a bird's eye view occupancy grid of the scene. And the catch here is you want to do what we call as amodal completion. And by amodal, we mean that you estimate things that are not obvious in the image. For example, if you're looking at this image and you kind of see this lane on the right that's merging into your current lane, and humans have the sense that there's not just a stretch of road, the pixels that you see in this image, but there should be like a stretch of road extending beyond. And we want perception models to now reason about this the stretch of road that's not visible in this image. And similarly, there's other common sense things like if this car stopped here, we'd reasonably expect to be like a stretch of road beneath the car. So we want models to hallucinate or like to estimate these layered representations of the scene, but not just things that are visible in the image, because they are fairly easy to do if you have like lots and lots of data and good models. But the hard driving decisions, they can only be made when you know more than what you just see in the image, like merging lanes and other driveways and so on. And we call this task amodal layout estimation and bird's eye view. And the challenge for this is because your task inherently requires you to reason about things that are not in the image, you don't have ground truth for these tasks. So you don't necessarily have ground truth for all of the lanes that are merging in. It's just hallucination that you need to rely on. So the key idea in this is, first, we generate like incomplete or partial, weak ground truth labels by aggregating data from multiple sensor frames. So you have a car that's moving, so you can take lots of LiDAR scans and then segment each scan and merge them. You get a fairly dense scan, but there's lots of holes and lots of edges that are not that are kind of improper. This only serves as weak ground truth because this still does not hallucinate, or this does not contain all of the information about roads that might be non-existent, but still in the area of interest that you want to reason about. So we also take rasters from OpenStreetMaps. So OpenStreetMaps give you, we just sample a bunch of road locations from OpenStreetMaps and how intersections look like. And those locations need not be aligned geographically with the locations you're actually testing in. So we just take a bunch of OpenStreetMap locations, rasterize them, and we then train a model that should, it should be faithful to the ground truth data, the noisy ground truth data, that noisy or partial ground truth data you have, but B, the layouts it produces should also be realistic. And by realistic, we mean that they should resemble the rasters you get out of OpenStreetMaps. So you should not have blobby roads with lots of missing chunks, because roads are usually contiguous stretches. And if you want to have an intersection, you need to make sure that the intersection looks like a plausible real intersection. And for that, we have like an adversarial regularization term, which basically means we have a discriminator that enforces the distribution of predicted layouts from the network to resemble the distribution of rasterized, perfect, nice looking OpenStreetMap layouts. And we find that this simple little training hack is enough to give us like plausible results. For example, you can see this sequence from the ArgoVerse dataset. When the car starts here, it's very difficult to see the intersections that are just going both sides of the road, on the left and the right. But there's enough visual cues for a human. For example, there's pedestrian crossing that you can use to reason, and there's like this slight gap between buildings with which humans can presume that there's going to be an intersection and then maybe slow down or switch to other forms of higher level reasoning, like to anticipate pedestrians and things like that. In our paper, we show a few applications, like particularly things like trajectory forecasting that improve because of the hallucination capabilities. But I'm not going to go into those details during the talk, but here's another sequence. So you can kind of see that the network hallucinates or predicts that there's going to be a turn, or here it gets another sidewalk even before it's actually clearly visible. But there's also a few artifacts because we rely solely on the RGB vision input. You can see a few artifacts from the shadows of trees. Network kind of believes them to be extensions of the sidewalk when they're not. So there's still a lot of work to do, but what we try to show in this work is you do not need ground truth annotations to actually produce plausible hallucinations of how roads might diverge and like to get these amodal completions in bird's eye view. All you need is like a good set of rasters from OpenStreetMaps, and you can still do a reasonably good job as you see here. And based on this, we went in just to see, at the limit, if you were given really accurate data, can you do a lot better? So for that, our more recent effort from IROS earlier this year was to create a benchmark. So we annotated whole sequences from the Kitty dataset for the task of amodal layout estimation. So you kind of have an image like this, and you would have a corresponding ground truth that corresponds to the amodal layout given this image or like a sequence of images. And we add lots of other information that might be useful, especially for driving tasks. So we have lane information and sidewalks, crosswalks, and other vehicles on the road. Now, one particular lane of interest is also the ego lane, like not just segmenting all lanes, but also for the perception module to keep track of what the ego lane is so that it helps in other driving decisions. So these are a few samples from the dataset. The dataset and the benchmark are publicly available at this webpage. And what we did once we had all of this data is we tried a bunch of existing approaches to see how they perform. Like all of the videos that I showed previously, they did not use any sort of temporal information. They were doing this on a frame-by-frame basis. But it's intuitive that once you start feeding it temporal information, it gives much cleaner predictions. And this is a sample sequence from the data set. So you kind of have this ego lane that the car is moving in red, and then you have the sidewalk in green. And this is what I mean by an amodal prediction. You want to have ground truth data that says, there's a lane that's about to approach. As humans, it's easy for us because we've driven lots and lots of roads. We can anticipate intersections, but we now need models that don't just anticipate movements of other actors in the scene. So there's lots of work on trajectory forecasting, like forecasting the behavior of pedestrians and cars, but we'd also like to forecast how scenes would look like a few frames in the future. And we also implemented a bunch of other baselines based on like existing popular approaches in the community, like the pseudo lidar class of approaches were largely successful up until a few months ago. So we had a few baselines on pseudo lidar, and then we had a few of our own extensions of like we had MonoLayout, which was the paper that I talked about earlier, and then we tried to extend that to video sequences to see if that improves performance. And in general, the task of Amodal layout estimation seems to work well at a level of predicting roads, but there's still lots of progress to be had in terms of predicting lanes and detecting vehicles. And we hope like this benchmark would be a good way for people to try their own approaches out. And like it'll also be an easy mechanism for getting into this area of Amodal layout estimation. So here's another example that I particularly like. So the blue line that you see here is kind of the ego lane. And you'll see that when the car turns to the right, it begins to sense that this is the new ego lane. So first, it gets this intersection really correctly, even before we navigate to that intersection. And once we turn into the intersection, it realizes that the ego lane is now changed and it's now this. And you also see that there were two lanes in here because this is a two-lane road, but then it gets onto this other street, which is a narrower street, no lane markings. So it just retracts to a single lane module. So overall, I hope from some of these, like over the last 15 minutes or so, I've given you like a little bit of foray into Amodal layout estimation, and like we've shown some applications of Amodal bird's eye view maps in our paper, and like including like object detection or trying to do object trajectory forecasting. So for the second half of the talk, though, I'm not going to be focusing on perception. We're going to switch gears and try and move to the full self-driving pipeline. And in this part of the talk, I want to focus on autonomous driving for rural roads. As I said, more than 70% of roads in the continental US are actually rural roads, and we want autonomous driving techniques that scale to these rural areas. And the key idea that I'll talk about in the remainder of the talk is, again, getting back to OpenStreetMap style maps. And we basically term these as topometric maps. So the idea of a topometric map is you have a topologically accurate map of the entire area, but the map is metrically inaccurate. What I mean by this is, if you look at intersections over here, for example, you know the topology of these intersections, whether it's like a three-way intersection or a four-way intersection or a two-way intersection or all of that, but you do not know exactly the metric properties of these intersections. So you don't know how exactly the distance between intersections or like exactly the width of the road and so on. And the idea behind the system I'll talk about, like we call that MapLite, is the way human drivers drive is they have a high level understanding of the route. So they know that at the next intersection, they probably need to take a right and then head straight on for two intersections and then take a left. That could be a sample driving instruction that a human has in mind. But between intersections, they tend to navigate more reactively. So they just react to the vehicles and road structure as the road curves and vehicles appear. So we want to see if this kind of a human intuition can scale back, like can be realized in an autonomous driving stack. And we do that by the idea or the notion of a topometric map. And topometric maps, because all you need, right, is a topology, but you don't need any geometric reconstruction. So they tend to be very, very easy to create. And they also tend to have a much longer shelf life, because geometric maps would go bad if you have vegetation that just keeps growing over seasons. But for topometric maps, a topometric map goes bad only when there's like a major change to a road topology, which happens far less frequently. And the storage size is incredibly small. For example, if you look at HD maps for a large urban area, you're talking anywhere between lots of gigabytes to a terabyte. But topometric maps, for example, the OpenStreetMap, just the topometric levels for the entire continental US is just about, I think, 80 megabytes. So you could essentially store the entire map in memory, not even on disk. The idea of the MapLite system, again, this was work led by Teddy Ort from MIT. And the idea of the system is you have local sensing. We have like a car equipped with a GPS, IMU, and a LiDAR. And you want to use local sensing to segment out a road. You want local perception. And then we have what perhaps the most important module here is the topometric map registration module, which takes the output of the segmentation module and tries to reconcile it with the topometric, like topologically accurate but metrically inaccurate OpenStreetMap. So you want to, this essentially serves the purpose of precise localization in HD maps. As opposed to that, we want to do this weak topometric localization using an OpenStreetMap. And then we have like planning and control modules. I'll go into details, perhaps not too deep dive, given that we have about eight minutes or so. So yeah, we have these planning and then control modules, which then execute actions. And this loop keeps repeating over and over again. So for the road segmentation module, we have these LiDAR scans, and we tried out a bunch of alternatives like various 3D point cloud processing architectures, as well as simplistic models like SVMs. And as I'll continue to show sometime later on, we found that SVMs offer nearly the same performance, but for a lot of reduction in terms of runtime. And I suspect that modern day neural nets, especially for images, might be faster. But in this case, since we had a lot of unstructured data like point clouds from a LiDAR scan, we found SVMs to be much, much faster. So here is like a video that's kind of showing segmentation. You can see that segmentation is noisy. You can see a bunch of road pixels being classified even off the road. So everything in gray, dark gray here is the road, and blue is not road. And especially in the initial parts, you can see road existing even outside. So we inherently have to deal with noisy segmentation and all other issues that crop up. Let's see. Oops. I hope. Oops, I guess I pushed the wrong button. Can you still see my screen?
No, I cannot see it right now. Maybe you need to restart sharing, I guess.
Yeah, let me just do that. Sorry about that. I just pushed the wrong button. All right, so I hope you can see my screen now. So we have the main module of MapLite is what we call a topometric registration module. And as I spoke about, the assumption is you have a good topometric map, but inaccurate metric map. So you know that there's going to be an intersection at some point, but you don't know how far you are off from the intersection. you probably have a good guess, but that's not precise. You can be like a lot of meters off, and in some cases maybe like even half a kilometer off, because even OpenStreetMaps for rural areas, they're not as precisely maintained because they rely on crowdsourcing, and population density in rural areas is not too much to hope for very accurate maps. So the input to this module is a topological prior map like the OpenStreetMap, and you get an initial localization, which is from the GPS. And the GPS localization, especially in the rural sites we tested in, it's not too accurate in that it also initializes us off-road a lot of times. And using the segmented LiDAR scan, we formulate like a cost function that registers and produces like this registered topological map. So I'll not go into the formulation, but this is like an optimization problem that we optimize over, like we want to maximize our observation likelihood. And once we have a good registration, we now want to have a replanning module. So in an OpenStreetMap, overall topological level planning is quite efficient. You can run any like your favorite graph search algorithm. And in our case, we really just used a simple A* graph search to get like a shortest route. But the idea here is we have this pre-planned route, and the map though is constantly changing because of the topometric registration. You might find the map keeps rotating in place and so on. So we have like a fast replanning algorithm that's detailed in the paper that only requires replanning if the vehicle deviates from the path. And if there's only metric level deviations without any topological deviations, we do not need to replan because that's likely due to an error in the metric level of the map. And we have like this trajectory planning module. The goal of the this module is to like plan a safe trajectory towards the goal. So you have like segmented road and you have an initial reference path. The reference path is almost always outside the road because the reference path is not accurately localized with the map. And the trajectory planning module comes up with a locally safe map given this reference map and given local perception. So you can see that as the car keeps turning here, the reference path keeps changing very frequently to ensure that the car is on the road and it does not deviate too much away from the center line. So I'll not go into the details a lot. It's again a variational planner with a few constraints, like you want to take a path with low curvature and you want that to be the shortest path and you want enough free space over either sides of the car. And you want to have enough goal points to be able to accomplish this. So yeah, we managed to get the system on a real car. This is an autonomous Prius V that you see here. And this is like a rural testing facility in Devens, Massachusetts. And we have like an RTK GPS for recording ground truth, but we do not use that for any other purposes except for evaluating, the accuracy of MapLite, for example, evaluating the accuracy of a human driver and so on. So the way we evaluate this is we have a chosen like test route with enough intersection traversals. So we have like 4 left turns, 3 right turns, and 3 straight motions at an intersection. So a total of 10 intersections and about 1.5 kilometers. And we do multiple repetitions of this run to get like statistically significant results. So that makes it a total of about 100 kilometers. And what we do is we first get a baseline traversal, and then we have the car drive itself by MapLite, and then we have a human driver, and we evaluate for both accuracy and repeatability. So how accurate is it to the center line of the road? And we also evaluate how repeatable is it over the course of 10 runs. So here's a short video of the testing facility. So this is mostly unpaved and like a single lane road. You can see Teddy in the car now, and this is now the car driving using the MapLite system. And once it reaches the end of, like once it thinks it reaches its goal, the system automatically asks for the next goal, and then he sets a next goal, and then this keeps going on and on. And we also measured the number of human takeovers encountered. So the first piece here is we evaluate the segmentation accuracy, and we see that the SVM has a far significant, it has significantly lower runtime for almost the same F1 score as a sparse ConNet. And the map registration module is, it seems to be the most critical module in all of our analysis. Like if you don't have a topometric registration module, the odometry estimate drifts quite a bit as you progress along the route. So this is again just a graph to show what would have transpired if you hadn't applied the topometric corrections. But since you apply the corrections, you get a really good fix. And in most cases, you're fewer than a meter away. And I think the highest error occurs presumably at turns when there's like a lot more scope for deviating off the center line. So we evaluate a few variants. So we evaluate a human expert, and we evaluate the MapLite system. And all of the rows below are the MapLite system without a few of these components. So we see that when you use the MapLite system, you do not need any human interventions, and you get a good enough accuracy. Like it's not as accurate as a human, but it's definitely more repeatable. So the precision score we compute is not related to the accuracy. Actually measures the accuracy with respect to a baseline route as measured by the RTK GPS. But the precision is more like how repeatable is this route. So if you use the MapLite system about 10 times, does it always take the same route? So it's like the root mean squared deviation across all of these routes. And we see that because of being like an autonomous system, MapLite is more repeatable. And then removing all of these components significantly deteriorates performance, especially the map registration module. And since it's not possible for at least an academic institute at this point to evaluate extensively on a lot of diverse scenarios, we conduct more studies in simulation. For example, all of these roundabout like scenarios in Carla, and you see that the MapLite system is kind of keeping the car on course, and it's doing all of this purely based on local sensing and like a weak topometric map of the road. So the benefits of the overall system are you don't need large scale geometric maps. You no longer need like these HD maps. Since the gathered information is really sparse, you can store maps for very large geographical areas almost in memory. And it's quite robust. Unless road structure significantly changes, you do not need to update this map. And the other level here is even if the vehicle gets lost, let's say you have an incorrect road structure and you get into another lane, the replanning will ensure that you will get back to the original goal. And even if you don't do so, you'll continue navigating safely. I guess I'm just a bit over time. So just the two real take-home messages I wanted to have are scale autonomous driving, especially to areas that are not urban centers. You need a a rethinking of what scene representations do we use when we want to make driving decisions. And crowdsourced maps can be extremely useful, not just for perception, but also for the full self-driving pipeline. And OSMs are just not the only solution, though. There's like lots of other alternatives. You can also think purely mapless driving, although I think we are probably several years away from realizing full mapless driving in arbitrary scenarios. So yeah, that's the thoughts I want to leave you with today. Happy to take any questions.
Thanks for the exciting talk. It's really cool to see you have the full evaluation on the real car, driving on the rural area, I guess. I mean, in academia, like you said, it's really hard to get that kind of resources, so it's really cool. I always want to do one, but I never get the chance, at least so far. Okay, so I guess right now we can take questions. If there are questions from the audience, you can just unmute yourself and ask questions. But I can start by kickoff. I guess we have time for maybe 1 or 2 questions. So first one is that when the first half of your talk talking about the model layout, right? You are using a single image or a sequence of images to do this online map completion from the bird eye view. And the second half of the talk is about, I mean, you are still doing something similar, but you're using scans. But in the meantime, you do registration and do planning on top. So I'm just thinking, it seems also possible that they use the model layout to do the registration, right? I mean, the second half of your talk, but just
True.
Using different online map completion or online map generation technique, right? It just replace of the first module you have in the whole pipeline. Is that possible, or did you try that? Because that's like even lightweight way of doing that. You're only using image, not even using point cloud, I guess.
Yeah, so that's really a great question. We've thought about this multiple times, and we've also like tried doing some experiments on these, but the real challenge turned out to be like handling a diverse range of environments. So in rural areas, you often have unpaved roads, and even during the MapLite project, we had to train models for multiple weather conditions. So for the first few months, we were testing actually in winter when there was like snow and ice on the road, and some of those models would not work when we tried it during summer or early spring. So we really found the perception gap hard to bridge at that point. So we tried to rely not on camera, but rather on like LiDAR, which is more or less, it's going to be slightly more robust in terms of getting the geometry of the road. There's also issues with LiDAR because the reflectance values actually change based on the time of the year. But since this was like, this project was luckily, or we had a lot of time spread across like 3 different seasons. So we had a large enough data set to like train models. So yeah, I think the perception, the image to layout gap is going to be the hardest to bridge when trying to like use that for navigation.
Got it. Yeah, that totally makes sense. I guess another small question I have, probably very quick, is that when you talk about the model layout, I mean, that video is really cool, by the way, but you said there's low ground truth, right? So you have to generate some pseudo labels. But when you, let's say, if we are using the new scenes dataset, for example, you already have the HD map. I mean, for any dataset with the HD map, is that like suitable for the ground truth, or?
So yeah, like for one of the data sets that we use, like at that time we used the Argovers data set because that was a data set with HD maps available. Yeah. So yeah, like for once you have HD maps with layer annotations, you're good to go. Like you could train these models end to end. Our thinking at the time was these are really laborious and expensive to obtain. Yes. Especially for other data sets that existed. Like for example, Kitty at that time had no HD variants with lanes and other semantic attributes. So that really was our thinking at the time.